Jai Hind, welcome to the course Network Analysis and Synthesis, and today I am going to discuss about the network analysis using the graph theory. So we have learned several techniques to solve a network, and we have seen that when the network is very large or very complicated, so we have to write a large number of loop equations based upon the Kirchhoff's current voltage law and large number of node equations based upon the Kirchhoff's current law. So it is a very tedious job to write the loop equations, large number of loop equations, large number of node equations, and to solve a circuit to find the current, voltage and power, what generally we do. There is another approach to solve a network using the graph theory. Although the graph theory is a separate subject, so we restrict ourselves to certain concept of graph theory to solve a network. So graph theory is a very systematic approach to solve a network when the network is very complicated or very large. So we will see later on what are those steps, how we will solve a network using the graph theory. So that is the outline of today, the importance of graph theory, why we are using the graph theory, because when the network is very complicated and writing loop equations and nodal equations are very tedious job to solve, write and solve is a very tedious job. So to get rid of those exercise, we follow the graph theory. Basically graph theory is a computer method. It is a computer method. We can feed some input in the computer, we can get the output. There is no any analytical exercise. We have not to solve the equations. Just write those equations in matrix form, feed the matrix in the computer, and computer give the result that we need, voltage, current, power, whatever. Then there are two techniques, loop analysis and node analysis. We generally in the conventional circuit using the Kirchhoff's current law, voltage law, we also apply these two techniques to solve a network using a graph theory. In the last week carry out some examples to solve a network using the graph theory. So when we apply the loop analysis and when we will apply the node analysis, okay. So it is convenient to write loop equation for a network containing voltage source but no current source. Suppose you are required to write apply the nodal analysis. It is written to solve this equation using the nodal analysis. So or loop analysis. Suppose it is given you have to write the loop equations. So loop equations we can conveniently write if there are no current sources in the circuit. So if the current source is present, then what we will do, we just convert these current sources into their equivalent voltage sources. It is convenient to write, and if there is any current source present in the network, for writing a loop equations, convert those current sources in its equivalent into its equivalent voltage source. Why we will do this? We will see later on the importance of taking the equivalent of a current source. We will see later on. Now look at, take any branch of a network. Okay, this is the one branch, and this branch is containing a voltage source Vs in series with impedance ZB. B stands for branch. Then there is a current. So I have taken one branch. In this branch there is a voltage source in series with impedance ZB, and there is a current source. So find the voltage across the point P and Q. So just write the simple line equations. The voltage at point P is, say, this is EP plus Vs, we are moving from minus to plus, and the current is flowing, so here is plus and here is minus, so minus ZBI equal to UQ is equal to 0. So EP minus EQ is this, and this is branch voltage. So this is the branch voltage. So this is the branch voltage of a network of one branch. I have written this equation for a single branch. Okay, there may be large number of branches, so you have to write the equation for each and every branch. So look at here, VV is equal to ZBIB minus IS minus VS. Now multiply both sides of above equation with tie-set matrix. So what is this? This is the fundamental tie-set matrix. Because I have straightway take I am straightway I am taking the help of this matrix. So if you want to learn about the what is the fundamental matrix, you have to refer my video lectures on graph theory. There I have explained all types of matrices, incident matrix, fundamental cut set matrix, fundamental tie set matrix. So we can refer. Here I am using this matrix. Okay. So multiply this matrix, fundamental tie set matrix, with these equations. You must be aware that the fundamental matrix, fundamental tie set matrix is applicable to a tree. What is tree? Tree is a subgraph of a graph which contains all the nodes but does not form any loop. So we select a tree, then the tree branches are twigs and remaining branches are links. So number of there are number of links are deciding the number of fundamental loops. So you understand, I hope so. So apply this. So Kirchhoff's voltage law in a loop is 0. So this fundamental tie set matrix into branch voltage is equal to 0. This relationship is also has been also proved. So 0 is equal to VF ZBIB minus ZBIS minus VA. Look at here. Now there is another relationship between the branch current and the link current. Suppose there is a graph. This is a graph. Okay, I am taking, just try to understand. This is the graph of a network. Okay, there are 4 nodes, 3, 4 and 1. This is the oriented graph. 4, 5, 6. Okay. Now to write a fundamental tie set, what we have to select a tree. So this is one tree of this graph. There are n number of trees. Okay. So this is one tree, and we can say they are the 3 and 2, 3 and 4. So these are the tree and these are the links. Okay. So how many links are there? There are 3 links. 1, this is 5 and this is 6. So this is one link. So one fundamental loop, another link, another fundamental loop, and this. So basically there are 3 links and there are 3 fundamental loops. So we can write the suppose matrix if you want to write. So this, suppose this is your L1, L5 and L6. Okay. Now the branches 1, 2, 3, 4, 5, 6. So L1, this is your L1, just nomenclature it, take the, this is L6. So L1 is 1, 2, 3. So the loop direction is decided by the orientation of the link. So it will be like this. So 1, 2, 3, 1, 2, 3, all are plus. Then L5. So direction of link is this. So orientation of the loop is this. So 5 is plus, 3 is minus, and 4 is minus, remaining 0. Come to this. So orientation of the fundamental loop is along the links. So 6 plus, 4 plus, 2 minus. So 6 plus 4 is also plus, 5 is 0, and 2 is minus 1. So this is the fundamental tie-set matrix you can write. If you can refer my video lectures on all the matrices, how can we write. So this is the branch current. Branch current means I1, I2, I3, and these are the link current is L1, L6 and L5. So this is the relationship between the branch current and link current. Branch current and the link current. Okay. Now look at here. There is one term. This is this. Okay. If you convert the current source into its equivalent voltage source, we can get rid of this matrix. This. If there is no current source present in the network, so this term will not exist. This term will not exist. So if we convert the current source into voltage source, we have not to do this exercise. So to get rid of this exercise, initially we convert the current source into its equivalent voltage source. So this is VL is equal to ZL IL. So this is the loop equations. Okay, for a single. So VL is equal to ZL IL, and ZL is BF ZB BF transpose. So what is ZB? ZB is the branch impedance of the network. So ZL is a loop impedance. This is the loop impedance matrix. This ZL. BB is the branch voltage matrix of order. So I just this will be in the matrix form. So BB will be the branch voltage if there are 6 branches. So B into 1, 6 rows and 1 column. I branch current matrix of order B into 1, number of branches into 1. This is the column vector. BS is also column vector, IS is also column vector. ZB is the branch impedance matrix of order B into B. So it is a square matrix. B is the number of branches. If there are 6 branches, so ZB will be the order of 6 by 6. Okay. We will just explain all these things with the help of some examples. Now what are the steps to carry out the loop analysis using graph theory? First, draw the oriented graph of the given network. Draw the oriented graph. Choose a tree if not given. So what? This is the oriented graph I have drawn up from the network. Choose a tree if not given. Write fundamental tie-set matrix. So 3 steps I have explained here. There is a graph of a network. Network is given. We have to write the oriented graph. Then take a tree and write this. So first 1, 2, 3 steps I have explained here. Now determine ZB. So write ZB impedance matrix of the network. Then we can find this ZL is BF, ZB, BF transpose. 3 matrices we have obtained. Write equations and then this. So these are the 6 steps. The very systematic. Draw the graph, oriented graph of the network, take a tree, write the fundamental tie-set matrix, write the ZB impedance matrix of the network, multiply all these three matrices and we get the loop equations. So, these are the very systematic. Now, come to the nodal analysis. So, node equations for a network can be written conveniently if it contains no voltage source. So, in the loop equations we have written if there is no current source. If the current source, voltage source is present, what we will do while writing the loop nodal equations, which convert voltage source into its equivalent current source. Now, take the branch, same here I have considered the YB admittance of the branch, which is YB is equal to 1 by ZB. YB is equal to 1 by ZB if the branch doesn't have any, branch have no mutual inductances. So, we apply this, otherwise we have to invert the matrices. Here, write the equations, same equations, this we explained earlier. So, this is the current. In the nodal analysis in terms of current variables, loop analysis in terms of the voltage. Okay. So, I is equal to this BV plus Vs by ZB, or I is equal to this. So, ZB is here I have written YB, it is the inverse of the ZB. Now, multiply both sides of the above equation with matrix A. So, A is reduced incidence matrix. Reduced incidence matrix. How will get it? Draw the oriented graph, write the complete incidence matrix and eliminate the last row of the matrix. The last row corresponds to the reference node of the network. Multiply both sides. So, what is this? This term is nothing but this is the Kirchhoff's current law. So, Kirchhoff's current law meeting at a, what it states that the current, algebraic sum of the current meeting at a node is 0. So, this is KCL, this is nothing but this is KCL. Put this on simplification, we get this. So, there is another relationship between the branch voltage and node voltage. So, if branch voltage is equal to the A transpose into node voltage. So, this is the relationship between the branch voltage and the node voltage. So, put here VB is equal to, we get this. Once we convert voltage source present in the network while writing the nodal equations, we can get rid of this exercise. Okay. So, it is why it has been written that it is convenient to write the convert the voltage source if present any into its equivalent current source. So, this is your node equations. This is the node equation. Node equation In is equal to Yn Vn. And how I will get Yn? Yn is nothing but A YB A transpose. So, write A matrix, transpose that matrix, then write ZB, and or we can write the straight way, we can write the YB. So, Yn is a node admittance matrix of order n minus 1 into n minus 1. Okay. Then A is the reduced or simple incidence matrix of order, because the one row has been eliminated. This is the branch admittance, node voltage, current source, voltage source. So, this is the vector columns, node voltage of this order, and branch admittance is a square matrix of V into B. Now, we can to carry out the nodal analysis, we can apply another approach. We have obtained this equations using the incidence matrix or reduced incidence matrix. We can write the nodal analysis, or we can carry out the nodal analysis using the cut set matrix. So, this is the alternate way of writing the nodal equations. In place of reduced incident matrix, we can write the cut set matrix. So, again this is the KCL, this is also KCL. Put this, and this is the relationship between the branch voltage and twig voltage. Twig voltage means branches of a tree are called twigs. Suppose there are 7 branches in the network and we have taken a tree branches, there are 3 branches. So, there are 3 twig branches and there are the 7 branches. So, this is the twig voltage. Relationship between the branch voltage and twig voltage. So, this way we can obtain this. So, this is the cut set admittance matrix. This is. So, for the carry out the nodal analysis, we either use the A matrix or cut set matrix. For carry out the loop analysis, we use fundamental tie set matrix. Now, do some examples. Very simple networks. Say here it has been written 2, 4, 5 as tree branches. So, this is the given network. Okay. Orientation is not given in these branches. So, we can orient this. Okay. So, first we can see here, see, look at, you have to write the loop impedance matrix. Loop impedance matrix means you have to write ZL. Loop impedance is tie set matrix ZB transpose. This. So, this is the basically loop analysis. So, to carry out the loop analysis, convert the current source into its equivalent voltage source. So, there is a one current source. So, convert this current source into voltage source. So, this is the circuit. I have converted this 5 ampere current source into voltage source. So, this is the circuit. Now, this is the circuit. Here we carry out the loop analysis using the graph theory. So, this is a oriented network. First and foremost, orient the given network. First orient the given network, then draw the oriented graph. Draw the oriented graph of this network. How many nodes are there? 1, 2, 3, 4. 4 nodes and branches 1, 2, 3, 4, 5, 6. 6 branches. So, just we draw this. This is the oriented graph. This is the step 1. Step 1, draw the oriented graph of the network. This, suppose this is node 1, this is 2, this is 3, because marking of node is important while writing the incidence or reduced incident matrix. Okay. Now, here look at, select 2, 4, 5 as a tree branches. Here it is mentioned that we have to take 2, 4 and 5 as a tree branches. It is written here, so you have to follow accordingly. So, now these are the tree branches. So, remaining branches are links. So, 1, 3 and 6, they are the links. Now, we can we can see that there are the 3 fundamental loops. Why 3 fundamental loops? Because there are 3 links. And the orientation of fundamental loop is same as its defining links. So, orientation of this loop will be like this, okay. This will be like this, because, and this will be like this. Now, you can write the fundamental tie set matrix. This is L1, L3, L6. This is the fundamental tie set matrix, okay. Now, take the transpose of this is the transpose of this matrix. Now, write the ZB. ZB is it is a square matrix of order 6 by 6 because there are 6 branches. So this is 4 is the impedance of the branch 1, 10 is the impedance of branch 2, this 10 is the branch of impedance 3, this J5 is the impedance of branch 4, branch 5 and branch 6. These are the diagonal elements we can see here. Here, look at here. Of diagonal elements are 0 because in the given network there is no mutual inductance present, there is no coupling between the branches. So off diagonal elements are 0. Okay. So these are the diagonal elements are the self impedance of the branch. Okay. First, second, third, fourth, fifth. So this is Z11, Z22, Z33, Z44, Z55, Z66. You can refer the network. So this is the ZB, you can write ZB. Now what you have to do, just write ZL is equal to, we have obtained this matrix, now ZB and BF transpose. So carry out the multiplication. So the BF ZB, so multiplying this matrix and this matrix we get this one. Now again multiply with this. So we get ZL. So this is ZL. This is the loop impedance matrix. So in the question, just loop impedance matrix has been asked. So we just finished here. If the loop equations, then we go for the VL is equal to ZL IL. We can go. Okay. We can obtain this. We can obtain all this loop currents. Now node admittance matrix and node equations. So this is the circuit to carry out the nodal analysis. So here we can see that there are current sources, no voltage source present in the network. So first draw the oriented graph of this network. This is an ideal current source, So element will be infinite, so it will be open circuit. So it will look like this. So this is the oriented graph 1, 2, 3, 4, 5 because these are the ideals. So no element is present in the graph of these ideal sources. So 1, 2, 3, 4. So this is the oriented graph. First, second step is take a because you are going to node admittance. There are two ways. Node admittance means YN. It is node admittance. So YN is A, YB, A transpose. Okay. So again it was, if we find the cut set admittance, then we go for the QF matrix. So for this case we just write A matrix. How will write? How many nodes are there? 4 nodes. 4 nodes are there, so 4 columns. Here is the fourth one. Okay. Fourth one is so 1 is between. So it is like this: 1, then -1, then 1, then 0, and then the 0. So this is the AA. This is AA matrix. A means include all the nodes, but I have written here the reduced incident matrix. So remove the last row from the network, from the matrix, to get the reduced. So in the reduced matrix there is three rows will be there because the 3 nodes. Okay. For the complete incident matrix there will be the 4 rows. So I just eliminated this eliminated. Now I have written A, then we can write the YB. So YB, this is the 1 1, this is 2 ohm, 2 mho, okay. This is the 10 mho, Y11 is 2, Y22 is 10, Y33 is 5, Y44 is J.25 and Y55 is minus J.5. So this way we can write the YB matrix. Look at here. So this is the A matrix, A transpose, this is the YB. Admittance. So in the network, admittance is given. If it is impedance, then we can write the 1 by ZB. So these are the diagonal elements. Off diagonal elements are 0 because there is no coupling in the circuit. So all of elements, off diagonal elements will be 0. So multiply this A transpose. So this is your YN. And this is your IN. IN means node currents. So this is minus A YB Vs plus AS. So there is no voltage source present in the network. No voltage source present in the network. So this is 0. So this is 0. So hence IN is minus A matrix into IS. IS is the column vector of the source. So there are two sources present. So 4 0 2. Multiply this, we get this. So this is your IN, this is your YN, and this is your VN. Okay. Now we have to find the node voltages V1, V2, V3. Just invert it. So it is inverted. So it is matrix of order 3 by 3. If the matrix is order 5 by 5, 6 by 6. So inversion is quite difficult. So what we do, just fed this matrix into the MATLAB. Moment we enter, we can get the result. So basically it is a computer methods, matrix form. Just enter into the computer, we can get the value of V1, V2, V3. So this way we can carry out the nodal analysis and loop analysis. So today just I have taken very simple circuit. This circuit has no coupling elements. In the next lecture we will carry out the nodal and loop analysis using graph theory for a circuit having the mutual inductances. So I stop here. Thank you very much. Jai Hind.